In 1869, Dmitry Mendeleev established the first official version of the periodic table of elements. Mendeleev found that when he sorted the elements by atomic weight, he found recurring patterns of chemical properties of certain groups of elements. Mendeleev's table in 1869 included a mere 63 elements, though, for many of the elements we know today remained either undiscovered or non-isolated, and therefore were unable to study. Mendeleev left many gaps in his table because of this, predicting that future discoveries of elements and their atomic weights would fill the missing spaces. This table worked well for a number of years, and many of Mendeleev's predictions came true. However, this periodic table was not perfect. For example, Mendeleev's table stated that nickel should precede cobalt because cobalt is a slightly heavier element, but their physical properties suggested that they should be swapped to fit in with their corresponding family of similar elements. Anomalies like these in the table puzzled scientists for a good number of years until a proposal made in 1913 by a young English physicist named Henry Moseley suggested that Mendeleev's table was sorted incorrectly. What Moseley proposed instead would lead to a redefining of the periodic table and the establishment of a new characteristic of atoms that is commonly used today to help understand the nature of the elements. Henry Moseley was perhaps destined for scientific greatness from the very moment he was born in 1887. He grew up in a rich aristocratic family. His father, Henry, was a professor of anatomy at the University of Oxford, and his mother, Amabel, was the daughter of Welsh biologist John Gwynne Jeffreys. Moseley had plenty of opportunity early and made the most of it, getting his bachelor's degree from the University of Oxford in 1910, and then moving to the University of Manchester to study under the one and only Ernest Rutherford. Rutherford had many students who went on to accomplish great things in science, and Moseley was no exception. While working under Rutherford, Moseley developed an interest in the study of X-rays, which was a relatively new field of physics at the time, as the rays were discovered less than 2 decades earlier in 1895. In 1909, British physicist Charles Barkla found that each element has a characteristic X-ray that electrons emit when transitioning from higher energy levels to lower energy levels in the atom's orbit around the nucleus. Moseley, after a few years at Manchester, came to believe that these characteristic X-rays could be used as a tool to analyze elements and their characteristics, and wanted to come up with a way to relate each characteristic X-ray to a physical property of each element. As it just so happens, a key discovery in 1912 gave Moseley the tools he needed to put his theory to the test, that discovery being Bragg's Law by Lawrence Bragg. The discovery of Bragg's Law in 1912 allowed an easy calculation of X-ray wavelengths based on how they deflect through crystals. Moseley was one of the first physicists to use X-ray diffraction to calculate X-ray wavelengths, doing so in 1913. Moseley set up an apparatus that allowed samples of metals to be bombarded with electron beams, allowing for the release of K-alpha and L-alpha X-rays, which would diffract through a crystal at certain incident angles. K-alpha rays represent a transition of an electron from the n equals 2 to the n equals 1 level, and L-alpha rays represent a transition of an electron from the n equals 3 to the n equals 2 level. He tested his apparatus on many elements of which many characteristics were already known, such as aluminum and gold, and what he found was a linear relationship between the element's atomic number and the square of the frequency of the emitted alpha rays. Before Moseley's experiments, the atomic number was essentially just an arbitrary number given to the elements, increasing by 1 on the periodic table per element, but there was no physical property that this number was attached to. With his discovered relationship, Moseley was able to link atomic number to a physical value and derive a relationship between an element's atomic number and the frequency of alpha rays it emitted. This relationship is known today as Moseley's Law. Moseley published his findings in 1913 in a series of 3 papers, suggesting that the periodic table perhaps shouldn't be measured by atomic weights, but rather by atomic numbers, which now had a measurable physical property. The data collected by Moseley heavily supported Rutherford's then new proposed model of the atom, which stated that the atom was composed of a positively charged nucleus. The atomic number quickly became defined as the amount of positive charge in the nucleus, and upon the discovery of the proton in 1919, further became defined as the number of protons in the nucleus. Moseley's atomic number fundamentally explained the unusual behaviors of Mendeleev's periodic table, such as the characteristics of cobalt and nickel despite their atomic weights, and also led to predictions of new elements that corresponded to gaps in Moseley's linear relationship. These gaps occurred at atomic numbers 43, 61, 72, and 75, and elements with these atomic numbers were discovered a few years later. Moseley's discovery of the atomic number put him on a fast track to win the Nobel Prize in Physics, but unfortunately that would never come to fruition. Upon the outbreak of the First World War, Moseley became inspired with a sense of British nationalism and felt it was his duty to enlist in the Royal Engineers of the British Army. He served as a technical officer of communications during the Battle of Gallipoli and was shot and killed by a sniper on August 10, 1915. Had Moseley not been killed in action, he most likely would have won the Nobel Prize in Physics the very next year, in 1916. The news of Moseley's death triggered an outlash amongst notable scientists, and they pushed to exempt scientific researchers from active duty in wars. This movement was headed by Moseley's mentor, Ernest Rutherford, who wrote in a letter, "It is a national tragedy that our military organization at the start was so inelastic as to be unable, with a few exceptions, to utilize the offers of services of our scientific men, except as combatants on the firing line. The loss of this young man on the battlefield is a striking example of the misuse of scientific talent." The movement did make some impact, as the British government assigned scientists to behind-the-lines work during World War II. Henry Moseley was a brilliant mind and a prime example of lost potential. Regardless, in his young, short life, he accomplished so much and is a prominent figure in scientific history. The relationship he established fundamentally changed our understanding of the elements, teaching us that the atomic number, not the atomic weight, was the key aspect of an atom that determined its physical behavior. If you enjoyed this video, please consider liking and subscribing. Click here if you want to see more scientific progress made during this time period. Thank you for watching, and I will see you in the next video.